Hi friends, in this session we shall discuss the important sampling distributions which we need for the interval estimation in the coming sessions. All of you are now familiar with the terms population, parameter, sample and statistic. But what is a sampling distribution? The distribution of a statistic is known as sampling distribution. For example, x bar, the sample mean, is a statistic. S square, the sample variance, is also a statistic. The distributions of these are sampling distributions. During our discussion in this session, we would be considering a population following normal distribution with mean mu and variance sigma square. Also, for the discussion on sampling distributions, we take a random sample of size n from this normal population. We know the probability density function of a normal distribution. It is f of x mu sigma is equal to 1 by root 2 pi sigma e raised to minus 1 by 2 x minus mu by sigma the whole square, where minus infinity less than x less than infinity, and the parameter mu is between minus infinity and infinity, and the parameter sigma is greater than 0. When a random sample of size n is taken from this population, let x1, x2, etc. xn be the sample values. x1, x2, etc. xn. These are the sample values. First, let us see what is the sampling distribution of the sample mean. Sample mean is x bar is equal to x1 plus x2 plus etc. plus xn divided by n. The distribution of the sample mean x bar can be derived using the moment generating function of the normal random variable. So, we use the moment generating function for finding the sampling distribution of x bar. The moment generating function mx bar of t is defined as expectation of e raised to t x bar. This is equal to expectation of e raised to t into x1 plus x2 plus etc. plus xn divided by n. Now, we know that x1, x2, etc. xn is a random sample. So, they are independent and identically distributed. So, this expectation can be written as expectation of e raised to t by n x the whole raised to n. Now, this expectation is the moment generating function of the random variable x, that is the moment generating function of the normal random variable. So, it is equal to e raised to mu t by n plus t by n square sigma square by 2 the whole raised to n. That is equal to e raised to mu t plus t square sigma square by 2n, which is the moment generating function of a normal random variable with mean mu and variance sigma square by n. So, by the uniqueness property of the moment generating function, it means that x bar is a random variable which follows normal distribution with the mean mu and variance sigma square by n. Now, we consider another sampling distribution called chi-square distribution. This distribution was introduced by Carl Pearson. It is actually the distribution of the square of the standard normal random variable. So, we consider the chi-square distribution. When x follows n mu sigma square, the random variable z is equal to x minus mu by sigma follows standard normal distribution, that is n0 1. A new random variable z square, the square of this standard normal random variable, that is z square is equal to x minus mu by sigma the whole square, has a distribution called the chi-square distribution. But since it is the square of a single standard normal, it is chi-square distribution with 1 degrees of freedom, and so we denote it as chi-square with 1 degrees of freedom. When chi-square is equal to summation I is equal to 1 to n xi minus mu by sigma the whole square, the new random variable, the sum of squares of n independent chi-square random variable, has a chi-square distribution with n degrees of freedom, and we denote it as chi-square with n degrees of freedom. To derive the distribution, again we use the moment generating function, that is the moment generating function of the random variable chi-square is m chi-square t, that is equal to m summation I is equal to 1 to n z I square t. Since these zi's are independent and identically distributed, we can write this as m z square t the whole raised to n. What is m z square t? M z square t is equal to expectation of e raised to t z square. So, we have to find out this expectation separately, and we will substitute those values or that value in this equation. So, we consider m z square t is equal to expectation of e raised to t z square, that is equal to integral minus infinity to infinity e raised to t z square into the density function of the normal distribution, and that also standard normal distribution. So, 1 by root 2 pi e raised to minus z square by 2 dz, that is equal to 1 by root 2 pi integral minus infinity to infinity e raised to minus 1 by 2 z square into 1 minus 2 t dz. Now, substituting z root 1 minus 2 t is equal to u, dz root 1 minus 2 t is equal to du, and hence this will become 1 by root 2 pi integral minus infinity to infinity e raised to minus 1 by 2 z square into 1 minus 2 t is u square, dz is equal to du divided by root of 1 minus 2 t. Again simplifying this, we get that is equal to 1 by root 1 minus 2 t integral minus infinity to infinity 1 by root 2 pi e raised to minus u square by 2 du. This part is the density function of the standard normal distribution, and hence the total integral will be equal to 1, and hence we get this as 1 by root 1 minus 2 t. Now, this is the moment generating function of a well known distribution. It is the moment generating function of the gamma distribution with parameters 1 by root 1 minus 2 t. Therefore, the moment generating function of chi square t is equal to 1 by root 1 minus 2 t to the power n, that is equal to 1 minus 2 t to the power minus n by 2. This is the moment generating function of a gamma distribution with parameters n by 2 and 1 by 2. The gamma distribution has the PDF f of x is equal to m raised to p by gamma p e raised to minus mx x raised to p minus 1, and its moment generating function is 1 minus t by m to the power minus p. So, here m is equal to 1 by 2 and p is equal to n by 2. Hence, the probability density function of the chi-square distribution can be written as f of chi-square is equal to 1 by 2 to the power n by 2 divided by gamma n by 2 e raised to minus chi square by 2 chi square raised to n by 2 minus 1, where chi square is greater than 0. So, here this is exactly similar to the gamma distribution. In the place of m we have 1 by 2 and in the place of p we have n by 2. Now, let us see the basic properties of the chi-square distribution. We have derived the density function. Now, we have to find out expectation of chi-square and variance of chi-square. To find the expectation of chi-square, we use the usual method, that is expectation of chi-square is equal to integral 0 to infinity. For the chi-square distribution, the range is from 0 to infinity, chi square into f of chi square d chi square, and that is equal to integral 0 to infinity chi square 1 by 2 to the power n by 2 divided by gamma n by 2 e raised to minus chi square by 2 chi square raised to n by 2 minus 1 d chi square. This is equal to 1 by 2 to the power n by 2 divided by gamma n by 2 integral 0 to infinity chi square raised to, combining these two terms, we have chi square raised to n by 2 plus 1 minus 1 into e raised to minus chi square by 2 d chi square. Now, this is again a chi square distribution. So, using the property of the density function, we can write this as equal to 1 by 2 to the power n by 2 divided by gamma n by 2 into gamma n by 2 plus 1 divided by 1 by 2 to the power n by 2 plus 1, which can be simplified as 1 by 2 to the power n by 2 divided by gamma n by 2. This part is n by 2 gamma n by 2, and here you have again 1 by 2 to the power n by 2 plus 1. Simplifying this, we get it as exactly equal to n. So, it means the mean of the chi-square distribution is n. Similarly, we can find out expectation of chi-square square, and in a similar way you will get this as n square plus 2n, and hence variance of chi-square is equal to expectation of chi-square square minus expectation of chi-square the whole square is equal to 2n. Therefore, the mean of the chi-square distribution is n and variance is 2n. Similarly, we can find out expectation of chi-square square, that is the second moment. It is equal to integral 0 to infinity chi square square into the density function, that is 1 by 2 to the power n by 2 divided by gamma n by 2 e raised to minus chi square by 2 chi square raised to n by 2 minus 1 d chi square, that is equal to 1 by 2 to the power n by 2 divided by gamma n by 2 integral 0 to infinity e raised to minus chi square by 2 into chi square raised to, combining these two terms, n by 2 plus 2 minus 1 d chi square, that is equal to 1 by 2 to the power n by 2 divided by gamma n by 2. Integral of this part is again gamma n by 2 plus 2 divided by 1 by 2 to the power n by 2 plus 2. This we get from the definition of the density function of the chi-square distribution. Now, this part can again be simplified, and that is equal to 1 by 2 to the power n by 2 divided by gamma n by 2. Gamma n by 2 plus 2 can be written as n by 2 plus 1 into gamma n by 2 plus 1 divided by 1 by 2 to the power n by 2 plus 2, that is equal to, these two can be cancelled, and that is 1 by 2 square into 1 by gamma n by 2 n by 2 plus 1. Gamma n by 2 plus 1 can be written as n by 2 gamma n by 2. Therefore, this is equal to this gamma n by 2 and this one are cancelled. It is n by 2 plus 1 into n by 2 divided by 1 by 2 square. That is equal to, simplifying, it is n plus 2 by 2 into n by 2 divided by 1 by 4. That is equal to n into n plus 2. Therefore, we got expectation of chi square as n and expectation of chi square square as n into n plus 2. This is equal to n square plus 2n. So, what is the variance of chi square? Variance of chi square is expectation of chi square square minus expectation of chi square the whole square, that is equal to n square plus 2n minus n square, which is equal to 2n. Thus, we got the mean of chi square as n and variance of chi square as 2n. Now, let us consider another statistic which follows chi-square distribution. We know that the sample mean x bar follows normal with mean mu and variance sigma square by n. Consider our usual transformation z is equal to x bar minus mu by sigma by root n, and this follows n01. Now, if we consider the square of this random variable z square, it will be x bar minus mu by sigma by root n the whole square is the square of a standard normal random variable, which follows chi-square with 1 degrees of freedom. Thus, we come to the end of this session. So, we have discussed the distribution of the sample mean and the sampling distribution chi-square in this session. Hope you enjoyed it. Thank you.